All right, let's just jump right in. Every single day, you make, I don't know, hundreds, maybe thousands of decisions, right? From what to eat for breakfast to which email to answer first. And most of these choices, they feel kind of intuitive, almost automatic. But what if I told you that hiding underneath all that intuition is this incredibly powerful logical structure? Well, today, we're going to unpack that secret language of decisions. Just think about it for a sec. How are you going to decide what to do later tonight? You've got options, right? You could go to a party, maybe head to the pub, or just crash on the couch and watch TV. What's your thought process? You know, you're probably asking yourself a series of questions, like, is there a party? If the answer is yes, cool, you go. If no, you ask the next question. Do I have a deadline? This whole flow of if this, then that logic, well, that's a decision tree. You're already a total natural at this, and you didn't even know it. And it turns out this very, very human way of thinking is also one of the most fundamental and honestly surprisingly powerful algorithms in the entire world of machine learning.
That's really it. I mean, forget all the complex jargon for a moment. All a decision tree really does is break down a big, messy decision into a series of smaller, much simpler ones. It's just asking a sequence of questions to get to an answer. Simple as that.
So to really get how this works, we got to break it down into its basic parts. Let's, look at its anatomy. Okay, let's use a classic example, deciding whether or not you should buy a used car. A decision process for that might look something like this flowchart here. Now let's pull apart the key components that you'd find in pretty much any tree like this one. So every tree has to start somewhere. That's the root node. If we look back at our car example, that's the very first big question you ask, like, is the car's color blue? It's the front door to your whole decision.
From there, your answer takes you down a path, or a branch, to a decision node. Think of this as just another fork in the road. It's a follow-up question that splits the path even further, like asking, okay, so if it's not blue, is it red?
And finally, eventually you hit a leaf node. This is the end of the line. It's not another question, it's the final answer. Buy the car or don't buy the car. Now this is the really crucial part. Decision trees are what we call a white box algorithm. You see, unlike some other machine learning models that are a black box, where, data goes in and an answer just pops out with zero explanation, with a decision tree you can literally see the logic. You can trace the entire path from the root all the way down to the leaf and understand exactly why a certain decision was made. This all seems pretty straightforward for a human, right? I mean, we do this all the time. But that brings us to the real mystery here. How does a machine, staring at a giant spreadsheet of data, figure out that is the color blue is the absolute best possible first question to ask? I mean, why not start with mileage or the year it was made? That choice is everything. And for a computer, it's not intuitive at all. The answer lies in a simple but totally brilliant idea, a quest for purity. The algorithm has one job, one single goal: to ask questions that split a jumbled, mixed-up group of data into smaller, purer subgroups. So, what do I mean by purity? Well, imagine you have a box of balls. If all the balls inside are gold, you'd say that box is purely gold. But if it's a mix of gold and silver balls, it's impure. It's the same with data. A group is pure if everything in it leads to the exact same outcome, like, say, a group where every single person ended up buying the car. And this is the whole game, right here. You start with a messy, impure group, and the algorithm's job is to find the one question that splits that group into purer, more predictable subgroups. The goal is just to make each new group less mixed up than the one that came before it.
So, how does it do this? Well, the computer doesn't just guess. For every single possible question it could ask, it calculates a score. This score is called information gain, and it basically just measures how much that one question helps to untangle the data and create those pure groups. And check this out. This shows you exactly what happens. The algorithm calculates the information gain for asking about the outlook, the humidity, and the wind. And what does it find? Asking about the outlook gives the most clarity. It causes the biggest drop in impurity. It's got the highest score. So the computer knows, boom, that's my root node. That is the best first question I can possibly ask. So the computer just repeats this process over and over and over, always picking the question that gives it the most information gain at each and every step. And that leads us to why this whole thing is so important. By repeating that same process at every single branching point, the algorithm builds a complete, finished tree. It creates an entire roadmap of decisions that it learned completely from the data.
And now it's ready. It's ready to make predictions on new situations it has never, ever seen before.
So why are these trees so popular? I mean, what's the big deal? Well, first, like we talked about, they're super easy to understand. They're that white box. But on top of that, they're also incredibly fast. They can handle messy data that has missing values, and they're flexible enough to work with all kinds of data types. They're basically the reliable, understandable workhorse of machine learning.
And that leaves us with a final thought. We use this exact logic for everything from predicting whether to play a baseball game to diagnosing diseases. It really makes you wonder, what if the most complex challenges we face in business, in science, even in our own lives, what if they aren't so complex after all? What if they're just a tree of simple questions, just waiting for us to find the right one to ask first?